Welcome to week 6, OS Security and Ethics. So, the foundation or the core principles of information security is basically lies in the CIA triad, where C stands for confidentiality, I stands for integrity, and A stands for availability. So, confidentiality is that you need to prevent unauthorized disclosure of the information so that unauthorized users can or the your information cannot be accessed to the unauthorized persons. Like for example, you use the encryption to ensure that only authorized users can read your data. On the other hand, integrity is protecting your data from unauthorized modifications or destruction. Like we use file hashes or the checksums to detect if a system file has been altered or not. And A stands for availability, that is ensuring authorized users have reliable access to information and systems, like denial of service attacks that make a service unavailable. So we need to defend against those using the availability. So confidentiality is only authorized users can read your data. Integrity, only authorized users can modify your data. And availability, to make ensure that your uh, authorized users get access to the data. Like if you know about the denial of service attack, so denial of service attack that you send so many fake requests said the original user did not get access to the resources, right? So the OS is the primary defender. Our operating system is the primary defender of the CIA properties for all the system resources. So the first pillar is the authentication. Authentication is the process of verifying the identity of a user, process, or device. Like, who are you? Authentication is who are you? Are you a legitimate user? Is the process is a legitimate process? So we know some of the methods. We use some of the methods for the authentication. Like we use the passwords or pins to make sure you are the legit person. So what is the role of operating system there? Operating system enforces password policies like length of the password, the minimum length of password, the complexity, like it should have some lowercase letters, uppercase letters, special characters, and expiration that after a certain time you need to update your password, right? So that is the passwords. Then something you have like smart cards, security tokens, mobile phones, so like for two-factor authentication, right? So we use these devices to for the authentication also, like we have a RSA device sometimes, the token we receive the token, and the same token we need to enter to verify that this is I am the authorized user. You can resemble it with the one-time password OTP you receive. So you receive OTP in your email, that means you are a authorized person because you are receiving that OTP. So, operating system provides drivers and APIs to interface with the hardware tokens, right? Then, how you can define the legitimacy of yours, or how you can define that you are authenticated? You can use the biometric devices like fingerprints we have on our phone. We have fingerprints, we have facial recognition, we have iris scan, right? So, how the operating system help in that? Windows Hello, Apple's Touch ID, Face ID are integrated at operating system levels for secure authentications. We can use multi-factor authentication also, which is a combination kindly of two or more methods. So it is very stronger in comparison to a single factor. Then the second pillar is the access control. Access control, that if you are okay, first pillar was if you are authenticated or not. The second pillar is access control, what you are allowed to do. If you are authenticated, what you are allowed to do, because it is not so that every user is allowed to do every operation. In a university there are some students, there are some professors, there is some other staff as well. Everyone does not have the same permissions. They are not allowed to do, all of them are not allowed to do the same operations. So that is the access control. So for that one, permissions. We have the permissions or access rights, that which actions are granted to a user, like read operation, write, execute, modify, full control, which permissions are assigned to a user. And other thing which we can do, we define the ACLs, which is the access control list. So ACL is a list which is attached to every object. It may be attached to a file, folder, or process. So it defines the permissions associated with that files, like which user has which permissions on this file. Okay, so and for this one, the models which we use, either we use the discretionary access mod control, DAC, or we use the mandatory access control, to which we call as MAC. So DAC is that owner of the object sets the permission, right? If I am the owner of an object, I will set the permission that what other users can perform what operations on this object. Whereas in MAC, the operating system enforces system-wide security policies and users cannot override it. So these are basically that these permissions will be identified by the operating system, not by the user. Whereas in DAC, these permissions or access controls are identified by the defined by the owner of the object. The third pillar is the encryption. Encryption is we convert our plain text into the ciphertext, which is an unreadable format, so that only the user who encrypts it or who knows the key to decrypt it, only they can access it, they can understand it. If someone else try to have this data, read this data, they cannot read it. So this is the, just to protect the confidentiality, we use the encryption process, which is converting the plain text into the ciphertext. So operating system provides some of the encryption technologies, like it do have the full disk encryption, file system encryption, full disk encryption, in which, as the name suggests, we encrypt the entire storage device. Like we use the BitLocker in the Windows, or in the Mac, we use the File Vault. So the benefit is it protects your data at rest. If your laptop is stolen or something, but your hard drive is stolen, your data is still safe. Your data still remains secure. On the other hand, file system encryption is it encrypts a specific or individual files or directories. Like you are just encrypting some, you're encrypting the file systems in Windows NTFS. So you're encrypting some particular files instead of the whole drive, the whole storage, right? So the operating system manages keys securely and often using a TPM, which is called as a trusted platform module chip. Then, what are the possible threats? The threats are, first type of threats are malware. Malware is the, it is a malicious software designed to disrupt, damage, or gain unauthorized access to a computer system. So the types of are, like we have a virus, which is attached to a legitimate program and spreads, and the operating system uses the antivirus scanners or code signings. Then another type is worm, which is a self-replicating malware that spreads over the network. For this purpose, we uses the firewalls, patching, and vulnerabilities. Then Trojan horse are the another type of malware which disguises itself as a legitimate software. So user education, least privilege. Then ransomware, which encrypts the user's files and demands for payments. So for that purpose, you need to have the backups, FDE, that is full disk encryption, and behavior monitoring. Then spyware is another type of malware which secretly monitors user activity. For this purpose, the operating system uses the anti-spyware tools and secure browsing. Rootkit is another type of malware, which is an operating system level threat. It hides deep within the operating system to avoid the detection. So for this purpose, we need to have a secure boot and integrity checkups and so on. Then another threat is operating system level vulnerabilities. So these are the flaws in the operating system itself and which can be exploited to violate the security policy. Like we have a, how can we have it like buffer air overflows, like a, if a program in C or C++, we can use the pointers. So for example, we can access the memory directly in C or C++, right? So a program writes data beyond the allocated memory buffer. So that is called as buffer overflows. When your program writes your data beyond the allocated memory buffer. So this can overwrite memory and allow an attacker to execute their own code. A primary target is the kernel here, which is the core of operating system as we know. Then another way is privilege escalation. It is a kind of exploitation that allows a user to gain higher level privilege. That is, from a normal user, you are given the rights of administrator or system level access. Then zero-day vulnerabilities, in which the flaws that are unknown to the software vendor and for which no patch exists. We call them as the zero-day vulnerabilities. Defense, the primary defense is patching. Operating system vendors release regular security updates to fix these vulnerabilities. Then, so how can we defend our system? Securing the operating system configuration. Hardening is the process of securing a system by reducing its surface of vulnerability. The key principles include the principle of least privilege, default deny, keep system updated, disable unnecessary services, use a firewall, and enable auditing and logging. So, principle of least privilege. Users and processes should have only given the minimum privileges which are required to perform their operation. Do not use your administrator account for your daily tasks. Always your administrator account should be different from your user account, and you should perform the operation by your user account, and the access rights to the user should be minimum. Default deny, block all traffic and services by default. Go in the system setting and block all the traffic and services and only enable those that are explicitly required. Do not let every service execute. Keep systems updated. Always automate operating system and application security patches. Just check on the regular updates of your system and regularly update your system. Disable unnecessary services. Every running service in a computer is a potential entry point. So turn these off when you don't need it. Like for example, Bluetooth, remote management, because by using these services, these are wireless services, by using these services, it is easy to have entry into your system. Then use a firewall. The operating system firewall controls inbound and outbound network traffic. So we should always use the firewall and enable auditing and logging. So what logging is, keep records of security events like who logged your system, how many failed access are there for monitoring and for all the analysis. Monitoring, the ethical issue. So the problem is the question comes, where is the line between legitimate oversight and an invasion of privacy? Like if employer monitoring, organizations monitor employee activity on corporate devices for security, productivity, and legal compliance. Right? Government surveillance, mass data collection for national security versus the right of privacy. So ethical questions here arises. What level of monitoring is transparent and proportional? How is the collected data used and stored? Does the need for security always outweigh for the right of privacy? Then another ethical issue is digital rights management, which we call as DRM. Again, the question here is, how do we balance protecting creator rights with the user freedom and fair use? Right? So, like operating system level technologies that restrict the use of copyrighted digital contents like movies, games, softwares. So, the creator argument is there that prevents piracy and protects revenue, ensuring creators can be paid for their work. That seems to be totally fair. But the problem is It violates the first sale doctrine. You can't resell a DRM locked game. Hinders accessibility, like screen readers may not work. Can punish legitimate customers while determined pirates bypass it. Give companies control over the device long after sale. Right? So these are the cons, the user arguments. Then another ethical issue is surveillance capitalism. The problem with this is the business model of harvesting and monetizing user data is to build into the modern operating systems and platforms. The model says if the service is free, then you are the product, right? So user behavior is tracked to create the targeted advertising profiles. The operating system role is to collect the telemetry data for improving the user experiences, and this data can incredibly detailed. The data it can be detailed data. The ethical questions here comes are: do users provide informed consent for this data collection? What are the implications for manipulations like micro targeting in politics? And who owns the data generated by a user's activity? Because the whatever activity you perform, whether on the network or internet, everything that all are recorded. Every user activity is recorded, right? So the conclusion comes here is it is the dual responsibility. Dual responsibility, technical responsibility and ethical responsibility. Technical responsibility is understand and implement strong operating system security practices like authentication, access control, encryption and hardening to protect systems and data. Whereas the ethical responsibility is critically evaluate and societal impact of the technologies we build and use. Advocate for transparency, user rights, and a balance between security and freedom. The security of an operating system is not just a technical challenge, it is deeply intertwined with the ethical choices. Then, we are going to discuss one more important topic in operating systems, which is process synchronization and deadlocks. It is one of the very important concepts, process synchronization and deadlocks. Now, what is the process synchronization? The process synchronization is when two or more processes are executing simultaneously, how they can be communicate with each other or how they can be synchronized so that the it do not interfere each other. The processes do not interfere each other. Let's understand it with the race condition problem. For example, processes often needs to share data like variables, file, database control records. When multiple processes can read and write this data concurrently, the final result depends on the order of execution. For example, the count plus plus problem. Let's say register 1 equals to count, that is the value of count you are putting in register 1. Then register 1 equals to register 1 plus 1, that is the value of register 1 is incremented. Then count equals to register 1. So the value of count is incremented by 1. If two processes P1 and P2 execute this count plus plus simultaneously, concurrently, the race condition can occur, leading to an incorrect value of count. The final result depends on which process finishes the last. So why is this hard? Because process execution can be interleaved in any order by the operating system scheduler. Like for example, only register 1 equals to count is executed by process 1. Register 1 equals to register 1 plus 1 is executed by process 1, and then process 2 try to read it. So it will read the old value of count. It is not incremented since it has not been assigned to the count again. So process 2 will not get the correct value. So the critical section problem is, so critical section is a segment of code where a process may be accessing the shared data. The shared data may be the files, memory variables, and anything. So we need to design a protocol so that when one process is executing in its critical section, no other process is allowed to execute in its critical section. This is the requirement of mutual exclusion. So, the solution requirements consist of mutual exclusion. That means only one process can be in its critical section at a time. Progress is if no process is in its critical section, a process must be allowed to enter. And then bounded waiting is if a process must only wait a finite amount of time to enter its critical section. That means there should not be any issue of starvation. So the first solution is the software solution, which is given by the Peterson's algorithm, and it is also called as the classic software based solution of two processes. So if you see here, we are, let's say, shared variables for two processes I and j, which are denoted as 0 and 1. Turn is a variable and we are taking a flag array of two variables and which are initialized with 0. So process pi's code. It may be process 0 or it may be process 1. Flag I equals to 1. That means if the value of flag 1 is 1, the process wants to enter the critical section. Turn equals to j. So the turn is set for the other process. While flag j and turn equals to j, it means it needs to wait if pj wants to add in and it's j's turn. Then critical section executes, then flag I equals to 0. That is, I am done. So now other process can enter its critical section. So then remainder of the section executes. So it uses the shared variables turn and flag to politely allow the other process to go first, ensuring mutual exclusion. The limitation of it is complex and does not work well for more than two processes. So we need to use the busy waiting. Then other solution is the hardware solution, which is test and set instruction. In this case, we require a hardware support in which we use the atomic hardware instructions. Atomic hardware instructions which are uninterruptible, which means if a instruction starts, you cannot stop in middle. You cannot interrupt it in middle. It has to be completed. So the definition for test and set instruction is given like this. The test and set, it takes a boolean variable lock. Original value of lock is set, then lock equals to true and return original. So do while test and set lock, acquire the lock, so it is the busy waiting. Do you see this semicolon? So it will go on, the while loop will go on continuously. It will check until it gets the lock. Then critical section executes, and once the critical section is executed, we set the value of lock as false, which means we are releasing the lock, and then remainder section executes. Atomicity, the entire test and set operation is executed without interruption. It is simple, verifiable, can be used for any number of processes, but it still uses busy waiting, which is wasting the CPU cycles. Then solution 3 is the by using the operating system, by using the semaphores. So a semaphore S is an integer variable that apart from initialization is only accessed through two standard atomic operations which are wait and signal. So, semaphore is basically an integer variable, okay, which can be accessed only through atomic operations, wait and signal. Wait S or P, wait operation decrements the value of S, and if S becomes negative, the process is blocked and added to the semaphore's waiting queue. So the definition of wait S is this. You decrement the value of S, and if S is negative, we block the process. It is added to the waiting queue. The signal S increments the value of S. If S is still less than equals to 0, a waiting process is unblocked. So we increment the value of S. If S is still less than equals to 0, wake it up or unblock the process, remove the process from the waiting queue. So We can use the counting semaphores for this one, and we can use the binary semaphores. Counting semaphores, which can have any integer value, can range over an unrestricted domain and used for resource counting. Binary semaphore are the integer value can have only values 0 and 1. So it is basically equivalent to a lock, either the process is blocked or unblocked, used for mutual exclusion. Then another concept comes is of deadlock. A deadlock is a state in which every process, if we are having the set process P1 and we are having a process P2, P1 requires two resources R1 and R2. P2 also requires resources R1 and R2, right? Now, but P1 has process R1 and P2 has resource R2. P1 is waiting for resource R2 and P2 is waiting for resource R1 because only then this process can execute. So P2 has R1 and is waiting for resource R2, and P2 has R2 and is waiting for resource R1. In this scenario, none of the process can complete because both of the processes are waiting for the resources which are acquired by other processes. Such kind of situation is called as deadlock. So a set of processes is in a deadlock state if every process in the state set is waiting for an event that can only be caused by another process in the set. There are four necessary conditions which are also called as Kaufman conditions for a deadlock to occur. The first one is mutual exclusion. At least one resource must be held in a non-shareable mode. Let's say if R1 and R2 are shared resources, then deadlock will not be here. So at least one one resource must be in a non-shareable mode. Hold and wait. A process must be holding at least one resource and waiting for additional ones. Like P1 is holding R1 and waiting for R2, and P2 is holding R2 and waiting for R1 in our example. No preemption. Resources cannot be forcibly taken away from a process. They must be released voluntarily. If P2 can forcibly take R1 from P1, then deadlock will not be there. So no preemption should be there. You process are not allowed to take resources forcibly from other process. And the fourth condition is of circular wait. A circular chain of processes must exist. Like if you see here, P1 is the circular. A circular chain should be there where each process is waiting for a resource held by the next process in the chain. Because as we say, P1 is waiting for P2 and P2 is waiting for P1, a circular chain. So which is called as circular wait. So all of four these conditions must hold for a deadlock to occur. If even one of the condition is not there, deadlock will not occur. So deadlock handling strategies. There are four strategies to handle the deadlock: prevention, avoidance, detection and recovery, and ignorance. Prevention is design the system to ensure at least one of the four necessary conditions is never met. That you are designing your system, as we said, these four conditions should be met to have a deadlock. If in our system, we design our system in such a way that at least one of the condition is never met, then deadlock will not be there. It is very restrictive, leads to low device utilization and reduced time throughput. Then another one is avoidance. Operating system is given advanced information about all the resource requests. It carefully schedules to never reach a deadlock state. Less restrictive than prevention, but requires knowledge of future resource needs. Then other one is detection and recovery. The operating system allows deadlock to occur. It then periodically runs an algorithm to detect them and once found, the system recovers by breaking the deadlock. Easy to implement, but recovery can be costly and complex. And the fourth one is the ignorance. Pretend that the problem does not exist. It is used by most modern operating systems for general purpose computing, justified if deadlocks are rare and the cost of prevention is very high. For the deadlock avoidance, we use one of the very popular algorithm, which is the Banker's algorithm. The key idea is deadlock avoidance, right? In which we need to give the advance information that about the resource request, that which process will require which resources and how many resources, right? So the key idea is each process must declare the maximum number of resources of each type it may need. The algorithm checks if granting a resource request would lead the system into an unsafe state. Unsafe state are those states in which it could lead to a deadlock. The request is only granted if it leads to a safe state. The key data structures which we use here in the Banker's algorithm for n processes and m resource types is available, max, allocation, and need. So available is a vector of length m resources indicating available instance of each resource type. That, like, I have 3 printers, 2 scanners, like that. How many resources of each type? Max, it is a n by m matrix where it shows the maximum need of process I for resource J. Like process 1 can require at most 3 resource of file 1 or like that. Allocation matrix is n by m matrix again. It is the current number of resources J allocated to the process I, and need is n cross m matrix, which is max minus allocation, that how many remaining need is there. So this is all about this week. Let's see you in the week 7. Till then, bye and take care.